And so a couple of examples here so that we can work with p-values. This is find the p-value for an alternative hypothesis that p, the true population proportion, is greater than 0.5 when we have a test statistic of z equals 2.11. Again, how do we find a p-value? It's a probability statement, and so I'm going to say it's the probability, and I've got to have three pieces here. Because this is a um, proportion problem, I know that my test statistic will be a z. I know what symbol to use because of the fact that I have a greater than alternative. That's a right-tailed test, so I'm going to say greater than on my probability statement, and then my test statistic is 2.11, and so that's how I write my probability statement. Something to take note of. Our alternative never has an equal to in it, but my p-value probability statement does. It's kind of weird. Why is that? Because if I roll back up here, the definition of a p-value is at least as extreme. Okay, and at least as extreme implies that it could be equal to that as well. Now we know that because the z distribution is continuous, when I work the problem, the or equal to doesn't matter. It's not going to affect any of my work. However, technically speaking, the p-value needs to have the or equal to in it. Okay, so it's kind of a weird quirk. You're going to have an alternative hypothesis that's greater than, and that means your symbol and your p-value is going to be greater than or equal to. You're going to have an alternative hypothesis with a less than, and your p-value is going to have a probability statement that's less than or equal to. Because the definition of a p-value says at least as extreme. That's inclusive of this number, even though it doesn't actually affect our math. It's just trying to make sure that we are keeping our T's crossed and our I's dotted. And now we work this problem just like we did way back in chapter 6. I don't have to standardize, it's already happened, right? That's the whole point of a test statistic, right? I standardized it when I found this. It's just I'm breaking this into its own individual piece. And so I don't have to standardize. I just get to go to my Z table once I have rewritten this as a less than, because I can't work with greater thans. My Z table and Excel both work with left tail areas, so I rewrite that as 1 minus. I look that value up in the table, and I can get my p-value like so. Next example, notice it's very similar. The only difference is now instead of having a right-tailed test, I have a two-tailed test. And so because I have a two-tailed test, what do I need to do with my p-value? I need to multiply it by 2. How do I know what symbol goes in the probability statement? It is not a not equal to. Notice in that flowchart that we have on the previous page of notes, there is no probability statement with a not equal to symbol in it. It always goes the same direction as the sign of my test statistic. My test statistic is positive, so that means I'm going to stick with the greater than or equal to symbol once I've multiplied by 2. Notice this multiply by 2 happens after I do the 1 minus, and so I'm going to notate here by this extra set of parentheses, I will have to do the 1 minus piece first, right? So then I look up 2.11 inside the table. We get a 0.9 something. Subtract that from 1 gives us that 0.0174. Multiply that by 2 to land at our answer. That's the basic setup for how to find p-values for proportion problems. What about with mean problems? What if I'm looking for the p-value for a mean problem where the alternative is mu less than 50? Notice the 50 or the 0.5. Notice it has no bearing whatsoever on finding the p-value. Why is that? Because this was already used when I found the test statistic, right? So once you get the test statistic, it doesn't really matter what the number is, right? This is only helpful to tell me what symbol to use my p-value. Here's my test statistic, negative 2.11 and an n of 14. Again, we have to have a value of n because we need to know our degrees of freedom. So my p-value statement is going to be a probability of a t, not a z, because this is a mean problem. We're going to say that we don't know sigma, and so we have to use S. That means we have to use a T. That's why we get our test statistic as a T here. It means we're going to say probability of capital T. I'm going to subscript it. with the degrees of freedom just to keep it safe. This is a left-tailed test, which means we have a less than in our probability statement. And now here's a difference between Excel and the table, is that with a Z-table and using Excel, you should get roughly the same answer. You might get a little more precise of an answer in Excel because you can use a Z value that has a third decimal place or goes off the table, for instance. So you can get a little more precise with Excel, but it's going to be more or less the same answer. However, when we're working with the T distribution, because the T table is wonky, it works a little bit different than using Excel. In Excel, you can find the exact values. Okay. On the T table, you cannot. On the T table, all you can do is say that the probability is between two values. So if you type this into Excel, you'll get the answer 0.0274. However, if you use a T table, all you can do is say that the p-value is between 0.025 and 0.05. And how did I get that? I first said if I have 13 degrees of freedom, I'm going to look at the row of 13 degrees of freedom. I'm going to ignore everything else because nothing else matters. That's the only row that matters. And what I'm going to do is I'm going to say I need to see where the value in question, negative 2.11, would fall in that row. Now remember, your T-table is everything right-tailed. It's all positive values for simplicity. And so we have a negative, so we're going to just ignore the negative, and we're going to say everything that's less than a negative works the same as greater than a positive. Okay, and so we're going to ignore that negative. We're going to see where would 2.11 fall, and we're going to say, oh, it's between two of these numbers that when I go to the top, if I follow those numbers up to the very top, in the part that says one-tailed area, I see that those numbers correspond to 0.025 and 0.05. Okay, and so that's how I can say that my p-value is between those two probabilities. Same idea here for a two-tailed test on mu. I have to multiply the p-value by 2. Again, do not use the not equal to symbol in the probability statement. This is a negative, so I'm going to stick with a less than or equal to symbol here. And it's the same value we found before, but times 2. And in this case, when I find those two values that I've bounded this 2.11 in my table between, now when I go to the top of the table, I use the two-tailed area row, and that should lead me to the values 0.05 and 0.1.